Now we're going to talk about another application of graph reductions and modifications. And this is a very straightforward problem. We just have a directed graph with edge lengths, but we're also given a subset of edges that we call risky. So some of these edges are risky, and our goal is to describe an algorithm that, given the graph, the edge lengths, and these risky nodes, as well as a starting node and some h, it will find for every node v the shortest path distance from S to v among all paths that contain at most h risky edges. So just the standard single source shortest path problem. So it's just single source shortest path starting from S. But now we're restricted in what edges we're allowed to use. We can use the risky edges, but we can only do it h times. So that's the main caveat in this problem. So there's two ways to do it. The first thing we'll try is dp, and we'll basically use the Bellman-Ford dynamic programming formulation to do this. So in this first strategy, we have our subproblems, d of vij. This is the shortest path from S to v that uses at most I edges in total, and specifically at most j of those total I edges can be risky. And we'll get almost identically the Bellman-Ford recursive formulation, which just have us, we can choose to use an edge, we can choose to just skip an edge. We haven't changed anything. We can choose to skip an edge and also decrease the amount of risky edges we can use. Or we'll try using a risky edge. That's what E prime represents. And if so, we've used up an edge, and specifically we've used up a risky edge, and this will be the total path distance. Otherwise, we use any edge that isn't risky, so we can keep j the same, but we still use one edge, u to v, to complete the path. So it's basically, if you just ignored these two cases, it's the same as Bellman-Ford, the dp formulation specifically. In fact, to compute the base case, which is going to be d of v n minus 1, 0, or in fact, any I, the base case basically is when h is 0, we actually compute this using Bellman-Ford, because this is exactly d of at most I of v. Okay, so we literally use Bellman-Ford to compute the base case, and then we use this recursive formulation that's almost identical to what Bellman-Ford did originally. The only difference is now we're keeping track of when we use a risky edge or not. And of course, if we run out, we can't use any more. And so we can only consider E minus E prime when we're doing this computation. At the very end, we just return d of v n minus 1h for all v's, maybe in a list, doesn't really matter. But the point is, just like in Bellman-Ford, we need to plug in n minus 1 there to avoid any kind of cycles. So remember, if there's negative weight cycles, then recursion wouldn't work. It'll just infinitely loop. And so having that n minus 1 there restricts the number of edges so that we never infinitely loop. So that's in particular why we couldn't do something like this, which might seem more natural because it could cause an infinite loop. And I urge you to think of formulating a version of this recursion where you use this kind of subproblem and try to think about where the infinite loop would come in. But the reason why we need it is for the same reason we did in Bellman-Ford, to avoid those infinite loops. Now, what's the running time? Well, we have I can be anything up to the size of v, which is n. J can be anything up to h. And then the rest of it is just the standard DAG dynamic programming. So we have v can take n values, and we look at all possible in edges, so it'll be O of n plus m. So there are n possible subproblems, but because we're summing up edges as well, overall we're doing n plus m times nh. But because in most shortest path examples, we just assume the number of edges is dominant, so we get this. Okay. So now, this is how we do it with DP, pretty standard approach. Now let's also think of how we could do it with graph reductions. So first things first, let's just remove risky edges. So this is the same as the graph V with E minus E prime. I'm removing the risky edges, and now I'm going to make H copies of G prime. And we'll call them G prime 0 to G prime H. And the idea here is G prime of each I is exactly, it's just literally a copy of G prime, but we're going to layer or stack these graphs. So we have G0 prime, we have G1 prime, and we'll have edges from one graph to the one beneath it. And we'll keep doing this. So let me move this one lower. So we have G, H minus 1 prime, and so on. So the idea here is everything in these are an exact copy of G prime. But then what are these extra nodes here, or these extra edges? Those are going to represent the risky edges. So these are the risky edges. So a risky edge, U to V, and E prime, now becomes UI to VI plus 1 in our new graph, which I'll call G hat. So G hat is just a bunch of copies of G prime, where in each individual circle there are no risky edges. So no risky edges in here in any individual copy. But there are risky edges between two copies. So the idea here is to move from one copy of G prime to the other, we have to take a risky edge. And because there's only H copies, we can only take, since there are H plus 1 copies, we can only take H total risky edges. So implicitly, every time we move down, our risky edge counter, or let's say our risky edge limit, goes down. And now we don't literally have a counter, but implicitly that's what's happening. Once we reach G H prime, so once we're here, we can no longer we can't use any more risky edges. So that's the idea. So if we compute the shortest path from S0 to everything in here, then that's giving us the shortest paths from S to V, where we use at most H risky edges. Okay, so now what are we going to do? Well, we're going to use Dijkstra to compute the distance function from S0 to everything else in G hat. And then what we're going to return is the distance from S0, the minimum of all of these, of all I, of distance S0 to VI for all V. So the idea here is for each I here, we're given the choice of how many risky edges to use. And so we're just going to pick the best one. So this picks the best number of risky edges to use. And it'll be at most H of them. Now, what's the running time of this algorithm? So the final min, that's just going to be a O of H for every possible node. So in total, the min part will be O of N times H. We loop over every possible node for every V, and also have to loop over every possible I, of which there are H of them. H plus 1 specifically, but O of H of them. So that part's O of N times H. And then to compute the overall Dijkstra algorithm part, well, that's going to be O of E prime, well, E hat log V hat. But how big are E hat and V hat? Well, there's roughly H times everything in this graph. So this is going to be O of H E log HN. That's going to be the running time for the Dijkstra parts, which is basically just running Dijkstra on every single copy. That's roughly what's happening. So overall, the NH factor doesn't really affect us, so we're going to get O of HE log HN. And if we just ignored this log H here, this is something like HE log N, which is better than the sorry, I should be using V here. This is better than the E times V times H we got using DP. So ignoring that small log of H factor, this will generally be faster. So you might be wondering, why is this faster? It's so much more complicated than the simple DP thing we did. And that's because the DP thing is solving a harder problem. Remember, the DP thing is based on Bellman-Ford, which is very general and can solve shortest paths with negative weights. Whereas this application, the problem statement itself said all the edges were non-negative right here. R plus means they're non-negative. And so really we could have used Dijkstra, which is much faster than Bellman-Ford because it's more specialized. So here, because we did this reduction this way, we got to use the specialization, the power of the specialization of Dijkstra. Whereas the other algorithm actually solves a more general problem. So that's why it's slower. but oftentimes graph reductions can be faster than the DP ones depending on the specific problem. So this is one possible technique, the layering technique that you can use in general when you're doing a graph reduction.